Hello, AP Calculus. I'm sorry I'm not there today, but the lesson must go on. Today we're going to talk about the precise definition of a limit, which really just brings together all the stuff that we've been talking about up until now. Nothing really new today, but we want to make sure that we understand exactly what a limit is. So let's explore again the idea of a limit given a graph. If I have some graph of a function, given some f of x, and given some point on the curve, let's say at A, and as we approach the x value A on the curve of the function, and we've seen that we can do left-handed and right-handed. As we approach from the right-handed side, as we approach from the left-handed side, we get closer and closer to some value L. And then we know the notation here. The notation we say is the limit as x approaches A of f of x is L. Now let's explore this point here, because as we'll see that it may not even exist here. The function might not even exist at A. So there's really three possibilities that I want to take a closer look at. First, first possibility, I have a removable discontinuity at A. But the limit as I approach the functions is still, even though this is a hole in the graph, I can still say that the limit as x approaches A of f of x is L, even though it doesn't exist there. Another possibility now here, again, it doesn't exist at A, f of A doesn't exist, but I'm going to make it exist. I'm going to fill the hole by giving it this value up here. So notice, as the function's getting closer and closer to A, the x value A, from both sides is getting closer and closer to the L value, although f of A is some other value up here. But we would still say the limit as x approaches A of f of x is L. The other possibility deals with asymptotes. We'll take a look at those in a moment, where A might be an asymptote and I'm going to infinity, increasing without bound. We'll take a closer look at that possibility in a moment. In order for a function to have a limit, we know that the right-hand side and the left-hand side both have to be approaching the same value. So again, I've got my function here, some point on the function A and L, and we know that we can approach it from both sides. So I can say that the limit as x approaches A from the left, from the negative side of the function, is the value L. And again, this is my function. This is the value L. Clearly that's happening here as I'm getting closer and closer. Also, as I approach from the right-handed side, the limit as x approaches A from the positive side of the function is also L, as I approach from the right-hand and the left-hand side. And we've already talked about that this both has to be true. If both of these things are true, therefore, I know that the limit as x approaches A of f of x is L. Whether there's a removable discontinuity here, or whether there's and it's defined somewhere else, it really doesn't matter. As long as both the right-hand side and left-hand side are approaching the same thing, then the limit as x approaches A of f of x is L. Let's take a look at an example where that doesn't happen, and we have to think about discontinuities. In this example, Again, I've got a function, but in this example, you can probably guess what's going to happen here. This is f of x, the whole thing is f of x, and this is my value a. So the problem here is I have this discontinuity. This was a jump discontinuity. And the reason this is a problem, there's no limit, is because as I approach from one side and the other side, I get two different values. For example, I can call this L1 and L2. And I would say that the limit, as I approach from the left, the limit as x approaches a from the negative side of f of x is L2, and the limit as x approaches a from the positive side of f of x is L1. They're approaching two different numbers. Now, even if I defined it, even if I plugged the hole here and defined the function to actually f of x to be L2, there still isn't going to be any limit. Therefore, the limit as x approaches a of f of x does not exist. It has to be approaching the same thing from both sides in order for the limit to exist. Now let's take a look at that possibility with infinite limits. Consider the function f of x equals 1 over x squared. We should know what this one looks like. This is one of our parent functions. It goes through the point 1, 1, negative 1, 1. And on this side, the function looks like this. And on this side, the function looks like this. And we have a discontinuity here. This is an asymptote discontinuity. But what about the limit? What's happening here for the limit? If I ask, what is the limit as x approaches, and we can see that 0, the asymptote, is the problem area of f of x, which is 1/2. Well, if I look at the right-hand limit and left-hand limit, the left-hand limit, as I approach from the left, it's getting larger and larger and larger. It's increasing without bound. As I approach from the right, it is also increasing without bound. So I can say that this function increases without bound. So I'm going to say infinity. Now, it sounds kind of funny saying that the limit of the function is infinity. You know, that just doesn't sound right to say it in English. So we would often say that it increases without bound. The limit increases without bound. We could say no limit, but don't get that confused with the limit does not exist. That there's no limit here. It increases without bound. But that is not the same thing as the limit does not exist. Those are two different things. Whenever we have the limit increases without bound or decreases without bound, then what's really happening at this point, and this would be my a value, what's really happening here is a vertical asymptote. So if this is true, if the limit approaches infinity, then I have a vertical asymptote. How would I write that down? I could say that the limit as x approaches a of f of x is infinite. If that's true, that would only be true if the limit as x approaches a from the negative side of f of x is infinite, and the limit as x approaches a from the positive side is infinite, and therefore we have a vertical asymptote. At x equals this a value, whatever that a value is. The same thing would be true if it was negative infinity. If the limit as I approached of some function from the negative side was negative infinity, otherwise decreasing without bound, and the limit as I approached a from the positive side was negative infinity, otherwise decreasing without bound, then the overall limit decreases without bound. It has no limit. It just keeps decreasing without bound, and that would be a vertical asymptote. The one that would give us a hard time is if this was mixed up, if it wasn't the same going both ways. And I think we know an example of that already. Consider the function f of x equals 1 over x. Have you had to stop the video yet to replay something because you didn't catch it the first time? Let me know about that tomorrow. I'm really kind of curious. So here, as I approach from the positive, the limit as x approaches, my a value is 0. That's the interesting value here. As I approach 0 from the positive side of f of x, 1 over x, it increases without bound. But as I approach 0 from the negative side, the limit as x approaches 0 from the negative side of the function, it decreases without bound, negative infinity. Therefore, the limit as x approaches 0 of this function does not exist. One way it approaches positive infinity, the other way it approaches negative infinity. Notice I don't have any problem approaching 1 or 2 or 3. These would all be nice values. And really what we want is the limit as x approaches the a value of f of x. We want that to be f of a, the value of the function at a. But here's where we see problems. All right, so there's no additional homework from 2.4. In 2.4, it really kind of sets up the idea as I get closer and closer what's happening. Let's just take one quick look at that. I'm going to draw a little bit nicer function here. And I want to take a closer look. Here's my function. And I've got some point here, a, and L. And what I want to do is I want to get closer and closer to this value. So I'm going to pick points on either side of A. So this point right here is going to be A plus some delta. A plus some delta. Oh, that's a terrible delta. And this would be A minus some delta. And this distance here would be the delta. So, and as delta approaches 0, as delta gets smaller and smaller and smaller, I'm getting closer and closer to the A value. And look what's happening to the corresponding limit. This value here would be L minus some epsilon, and this value here would be L plus some epsilon. And as the delta value approaches 0, the epsilon value also approaches 0. So as I get closer and closer and closer, as I approach from the negative side, here I am getting closer and closer and closer from the negative side. And as I approach from the positive side, here I am getting closer and closer to the positive side. This point right here. And again, remember, this could be a removable discontinuity, or the function could even be defined somewhere completely different. It doesn't matter. As the deltas get smaller, the epsilon gets smaller by a significantly close enough number. There's a whole formula for this. There's a whole formula for how big the delta has to be in order for there to be a limit. We really don't need to get that far into it. We've already seen the tricks of what happens if we can't do direct substitution and infinity and the other things. So I think we're okay on the idea of a limit and all the different ways to find a limit. It's a small part of the AP test. They'll definitely talk about using limit laws and so forth on the AP test. Tomorrow we're going to talk about continuity, and I'm going to talk about where a function is continuous. And we've already seen that if there's a hole, in other words, a removable discontinuity, it still could have a limit. Well, what does that do to our differentiability, the slope of the tangent lines there, especially if the point was defined somewhere else? Clearly, if it's a jump discontinuity, or if it's an asymptote, we can understand what's going to happen with the tangent lines there. But how does discontinuity play a role in that? And we'll explore that tomorrow. All right, well, let's see. What else is there to do today? Oh, yeah, pop quiz. All right, ladies and gentlemen, we're going to have a pop quiz. Don't panic, don't freak out. It's going to be open notes with a calculator. I know. I think the quiz actually says no calculator, but we can do it with a calculator. So, Mr. Beal, if you would turn off the video and then give them the quiz. Thank you very much. I'll see you tomorrow, guys.